So welcome. This is what we call the Advanced Manufacturing Lab. It actually houses Professor Xiaoshen Li and my facilities. We share the space. This was the machine shop space in the original building. When it was renovated and things moved around, we were lucky enough to get this space. The activities in here are split up a little bit. In here, we have laser-based manufacturing work that both of us do. And I will let Madhu, one of the grad students, briefly talk about micro laser polishing work that Professor Lee, Neil Duffy, and I work on together, and he's doing for his research. We also do micro end milling work. Here's a micro end milling machine that we use. Chris will talk briefly about the diamond coating. We grow or synthesize our own nanocrystalline diamond coatings using chemical vapor deposition over here. And then Professor Lee and/or his student will talk about some very exciting nanocomposite work that he's working on.
Hello everyone. So as Professor Fefrikon said, I basically do my research work on this table, right? So the basic setup is we are trying to use a laser to melt the upper layer of a surface at micro level so that we can smoothen the irregular surface features on that, right? Right now we have a Lee laser. It's an ND-AG laser. It's about 1064 nanometers wavelength. Right, we pulse it at about 300 nanoseconds to 650 nanoseconds. So basically, that's the pulse width of the laser. You just see an optic system which just guides the beam into the scannet. It's a very high-speed scannet. Basically, has a 2-axis mirrors inside, galvanometers, which basically direct the path of the laser beam onto the sample. On a Z stage here, where we can actually adjust the focus, the distance from the focus on the system. We also have the facility of an argon shielding so that there is no oxide formation on the samples that we use.
So we have been working on that field of micro nanosensors for process monitoring and control. Martin also one of the collaborators right now. So we have been working on micro nanosensors, try to utilize the micro nanosensor to harsh engineering environments, such as manufacturing process. Because a lot of micro nanosensors utilized in electronics industry or clean environment, right? So all the sensors that are successful, very good response. But the one shortcoming they always come up is they cannot survive high temperature. They cannot survive in very harsh, very abrasive environment like manufacturing. Right? So normally when you talk about micro nanosensors in the silicon wafer or computer chips, when you talk about high temperature, they say 125 degrees Celsius is the temperature limit they can go. But for us, for manufacturing guys, we regularly cutting 600, 800, 1000 degrees Celsius all the time. Right? The sensor cannot survive that. So that's why we think about to integrate thin film micro nanosensor to the manufacturing process. And the one strategy to make them successful to embed it, because any surface exposed the thin film sensors will get killed, right? Will get killed very quickly by the process. And if we embed into the materials, so-called structurally integrate micro nanosensors, right, to the structure like we did, you can see later on, you can see all the sensors embed to metal or to the ceramic toolings, like we also have here is before the embedding sensors and after embedding. So this one can use as cutting edge, right, the sensor very close to the tool workpiece interface. And we really can get our sensor as close as 20 micrometers away from the cutting edge. Traditionally, the best in the world, you can get into about 500 microns. Okay, so because you get less than 500 microns, your sensor gets too noisy. It just cannot function well. And our sensor, just recently we demonstrate we can do that.
One of the work that we do in the micro end milling realm here is look at diamond coating, very thin, conformal and continuous diamond coatings The main reason for going thin is to not blunt the edge radius or whatever features we put on the tools. We grow our own diamond coatings in here. The reason they're nanocrystalline is we're trying to make 100, 200 nanometer thick coatings. We need to be able to grow small crystals with that. We have a small chemical vapor deposition reactor. It's just a very small system for research. We generally grow on one tool at a time. However, this process, as you may or may not know, is completely scalable. They're commercially available 16-inch diameter chambers where one could put hundreds of certainly micro tools at a time and coat them. You flow in methane, excess hydrogen, just 4 to 6% methane hydrogen in here. Tungsten filaments, just like the old light bulbs here, we get them to about 2,000 degrees Celsius to dissociate those gases. All right. And the radiation from them heat the substrate, in this case a micro end mill, and then the gases come down under the right pressure, gas mixture conditions. When they hit the surface, the hot surface, chemical reactions occur, and ultimately what we're looking for are diamond bonds forming. And so literally it is a, atom by atom, in that sense, process of synthesizing or growing this diamond film on the coating. So we do this in-house with our collaborators. This project is in collaboration with Dr. Karpik at Penn, University of Pennsylvania, and Dr. Suman at Argonne National Labs. One of the great things that we found in microannealing is the low friction and the low adhesion of materials to diamond. Why? I mean, diamond bonds are very strong. Unless you get a dangling bond out there, they don't want to attach to other things. That's why you get low friction and low adhesion. And this has great benefit as we shrink down. We get more surface area for the volume we're trying to cut, and so it helps a lot. Even with something as easily machinable otherwise as aluminum, we can see sometimes significant force reductions when we're micro end milling with the diamond coatings because there's less adhesion. And also, a big thing, the chips don't stick in the flutes. I mean, not even just talking the cutting zone, but evacuating material up the flutes of the micro end mill.
So in here we work on metal matrix nanocomposites. So we're taking lightweight aluminum and magnesium alloys and pure metals and then adding nano silicon carbide or other ceramics into them to create a strong matrix or a strong composite material. And recently we found that we can double the strength of the matrix material with just a 1% volume addition of the ceramic nanoparticles. And when you compare that to conventional metal matrix composites where you put in, say, 20% of 10 micron or so size silicon carbide pieces, we get better strength enhancement, but we also don't pay a lot of the penalties that you typically see with metal matrix composites. Normally when you put 20% silicon carbide into an aluminum, you make your material that was once very ductile, very brittle. You also make it very difficult to machine. With these small additions of nanoparticles, we can enhance the strength even more so than the conventional composites without having to pay any ductility or machinability penalties. When you make these materials, the real trick is getting the nanoparticles broken up and well dispersed into your material. Due to the high surface to volume ratio of the particles and the high associated interfacial energy that you create as you disperse the particles, the nanoparticles really like to agglomerate and they really don't want to break up and disperse into your material. To overcome these problems inherent with nanocomposites, we use an ultrasonic technique to break up the clusters. The ultrasonic energy creates cavitation events in the melt. These break up the clusters. It also creates a streaming or sort of a bulk flow of the material, and that then serves to distribute these now broken up nanoparticles into the melt. And then we can cast it. A lot of nanocomposite processes are either powder-based or severe plastic deformation based, where you're very limited in the geometries you can create. And as far as the powder metallurgy goes, it's also very expensive and time consuming. By using a liquid process, we still have our geometric flexibility and also can do it quite rapidly. So there's a tip that goes on here that actually extends down and dips into the melt. That then creates the cavitation and streaming in the melt that brings in the particles as well as breaking up the clusters of the particles.
So that's what disperses the
Right, that's what disperses the nano ceramic phase, yeah.